Hello, everybody. It's me again, Rich Andre. And today we're going to be talking about, this is going to be the part three and probably the final part of the gas laws series that I'm making. So this is going to encapsulate the ideal gas law, Dalton's law, law of partial pressures, and Graham's law of diffusion and fusion. So let's start with the ideal gas laws. Here we have a few problems, that we need to solve, and let's do just that. Okay, let's solve some ideal gas law problems. But first, I want to explain what the ideal gas law is in general. Okay, so the ideal gas law. Let's go back to the four fundamental sort of parts of gases. Okay, so we have volume, pressure, temperature, moles. Now, if you have all of these, okay, what we're going to be expecting from the ideal gas law is that Charles' law, Boyle's law, okay, Charles' law, Boyle's law, and Avogadro's law. That's basically just the ideal gas law. Okay, and the ideal gas law basically just stipulates that all of the gases has no forces on them, and every single particle is moving as it's supposed to, or as it's expected to. That's basically what just the ideal gas law is. So first, we have to know what the formula is in order for us to solve our problems. So we have PV equals nRT. And now we have to explain what these capital letters denote. So this is pressure, this is volume, this is amount of moles, and this is the gas constant. Take note that the gas constant is always changing, okay, depending on what is being asked. Okay, so but generally the gas constant is this. Let me just see this. Yeah, the gas constant is equal to 0.80 uh 0.82057. That is the the gas constant. Okay, generally speaking. So we have T, which is basically just temperature. Now that we've denoted everything that there is to excuse me, know about the ideal gas law, we have to solve some problems. Okay, so first we have the problem here. Let's copy and paste that. Okay, so we have this problem. A gas occupies, let me just copy and paste everything so we don't have to keep keep reopening ChatGPT here. What what the hell happened? Okay, we can do this. Hold on. All right. So we have this. A gas occupies 8.20 liters at 2.50 atmospheres and 27 degrees Celsius. So let's first write out our given. We have the given here. Uh, what is P, V, N, R, 0.82057. This is the gas constant. That means it's never changing. Okay. And I believe it is like this as well. Wait, let me just see the gas constant. The gas constant of air is here. Okay, so we have L liters over mole in K, mole and Kelvin. So these are going to change depending on what's being asked. Okay, so we have the volume, which is 8.20, number of moles, which is not included. So we're basically just going to find that. Just just go drink some water. So now that we have this general formula, okay, now we're trying to find how many moles of gas are present, so we can use this formula. N equals PV over RT, okay? So substitute with the values here. We have 2.5 atmospheres times volume, which is 8.20 liters, over gas constant, which is 0.82057 liters in atmosphere over mole and K. Mole and K. Okay, so we have these times what is DT? What is the temperature? We forgot to include the temperature. So it's 27 Celsius. 27 Celsius plus 273.15, which gives us this. Okay, so how many moles of gas are present? Obviously, we're going to use a calculator for this. So 2.50 times 8.20. Okay, 8.20 over 0.82057 times 27 plus 273.15. And we gonna have a total of 0. Okay, so we're gonna have 0.832. So we just have to remove all of the cancel all of the stuff here. Considering this is going to be K, the only thing that's going to be here is this, the moles. So we have 0.832, okay, 8323. That's going to be mole. Let's see if our answer is correct. Let's see if our answer is correct right here. Answer sheet is 0.833 moles. So I think there has to be some sort of mistake here. I don't really know. 0.833. How did I get 0.833? There has to be a mistake with the gas constant because everything so far has been correct. Yeah, there has to be. So let me see the gas constant. I see. The universal gas constant value. Okay, so then must I use something else for the universal gas constant value? 0.808205. Let's try removing the 7 here in the gas constant. Must have been ChatGPT. I was only using the example ChatGPT gave me with the gas constant. So let's remove that. And we will be correct, you know. Our final answer would be 0.833 moles. Okay, that's going to be final answer. Mole. Just mole. Just mole. Not moles. Either way, we're going to go do another problem. This is going to be varying problems. So now we have this. Container holds 3.00 mole of nitrogen gas. So PV equals nRT. What are we trying to find? The volume. So then we're just going to have nRT over P. That's basically it. So then substitute the values. You get 3.0 times R 0.80 8205 0.8205 8205 liters and liters. What was it? ATM and mole. Okay. CRT. What is the temperature? That's going to be 25 Celsius. 25 Celsius plus 473.5. Let me just 25 Celsius plus 373.15 and this over P. So what is the pressure? We have 5.00 ATM. Now let's cancel. Okay, let's cancel some. Let's cancel. Mole. And we're trying to find a volume, so it's going to be canceled as well. Then we just have to calculate, you know. Yeah, 3.00 times 0.8205 times 25 plus 273.15 over 5.00. So we have a total of 146.678. 46.78 liters. Is that correct? Let's recheck. Yes, I believe that would be it. Let me just check. Wait, 14.7 liters. How is that possible? I did everything right. Times 0.8205. What is 8205? Zero. Oh, I forgot a zero. I forgot a zero under constant. Yes, constant. That's going to be 14.7. 7 liters. My bad. I just forgot. I just forgot a zero here on the gas constant. So that's going to be 14.7 liters. You know? So let's do number 3 here. We get the general idea of this, but I'm just going to be inputting everything, okay, into my calculator directly. But of course, we're going to depict the general sort of solution or the formula. So we're trying to find pressure here. So PV equals nRT. Trying to find a pressure. It's going to be nRT. Okay, V. So just going to be it, you know. Now we just calculate. So zero, we have 0.750 moles times the constant 0.8205, 0.08205. I should never forget that, times T, which is temperature here. So we have temperature of 30 Celsius plus 273.15 over what is the pressure? Okay, so the volume is going to be 15.0 liters. Okay, so our pressure is going to be 1.24 okay, atmosphere. That's correct. So let's do the number 4. So we're trying to find the temperature, and if we do this and RT, and we just completely ignore everything, so we have T equals PV over NR. Okay, this is going to be it. I believe that is it. Okay, if we're wrong, then we're wrong. We just have to correct. So we have pressure 1.28 atmospheres times 12.0 liters. This is the volume. We have 12.0 times over NR. So we have 0.600 times 0.08205. Then we're gonna have 2.92, 292.50 in Celsius. Okay, so obviously this is going to be in Kelvin. I believe this is going to be in Kelvin. So given that, we just have to minus 273.15. We're gonna get 292.50 minus 273.15. We're going to get 19.35 Celsius. So let's check. Why is it 20 Celsius? I have 19.35 Celsius here. Let me just check again. Let me just try again, okay? Let's try again. So we have this atmosphere. We have 1.20 times volume, which is 12.0 times over NR. And NR, which is 0.600 moles. Then we have R, which is 0.082. 0.08205. Is 273.15. There has to be something wrong here. It says here it's 20 Celsius, but I'm getting 19.35. Let me see the ideal gas law. Maybe the formula isn't correct. Temperature formula. Let's see the temperature formula right here. Maybe they're using 0.8206. There's a chance, but let's check it again. So let's try 1.20 times 12.0 over n, which is 0.600 times 0.08206. Yeah, we minus that by 273.15. Oh, shoot. It's really 19. It really comes out as 19. Let me try asking Gemini. T, so it's right. T equals PV over NR. His answer 20 Celsius then. Everything is perfect. And then the answer's, yeah, we're just going to skip that because everything has been perfect so far. And we can't round it. We can't round 19.35 to uh 20 Celsius to 20. So we're just going to skip that. Maybe ChatGPT is the one wrong. There's a chance. So we have determine the pressure. Again, this is going to be, yeah. So let's do it. Let's do number 5. 20.0 moles. 0.08205 times T, which is temperature 25 Celsius, plus 273.15 over V, which is going to be volume, which is 15.0 liters. So we're just going to get 32, 32.62 atmospheres. I believe that is it. Let me see. 30, yeah, 30.6, 32.6 atmospheres were correct. Let's go do the sixth number. Okay, so how many moles of, so what, we're trying to find moles. I'm just going to, if we're trying to find moles here, we have RT, PV. So let's do this, you know. Pressure is 0.950 atmospheres times volume, which is 45.0 liters over, which is R time R and T, which is what is R? 0.08205 times the temperature, which is 550 plus 273.15. 273.15, and we're going to have 1.61 atmosphere. Yeah. What? Wait. Oh, I forgot it was moles. It was actually moles. So 1.61 moles. Okay, so let's do number 7. After we're done with everything here, okay? After we're done with everything, I'll try to get the, because we already have like n here, and I'm trying to understand if what if n isn't given. Instead, the unit you use is something else. Like let's say just something else, and then we're going to translate it. we're going to translate it to n. Then there's stuff like, wait, let me just go get my notes after I finish these problems. So we have this, which is PV equals nRT. So number of moles, RT and PV. So let's go do it. PV over RT, and then pressure. What is pressure? 3.20 atmospheres. Volume 6.00, and then over R, which is 0.08205. 0.08205 times T, which is 400. So we have 0.5850. 0.5850 moles. Yeah. So let's go do that. Let's go do number 8. We'll try to make this faster, you know. I guess. Okay, so we have P. Let's find the pressure of PV and RT. We're trying to find pressure, so we have P, V, and RT. Okay. So just have this N, which is 2.50, times R, which is 0.08205, times T, which is 350K, okay, over what? We have volume, which is 330.0, and then we're gonna have 2.39 atmospheres. Yeah, so let's go to number 9. 2.39 atmospheres. So then we have this. I guess 10.0. Okay, so we're trying to find new pressure. So we're trying to find pressure. So then we just have to do this, you know. So nRT, what is N? The N is the changing amount of gas or volume. So then the amount of gas is going to be 1 atmosphere, because that is the standard atmosphere. Okay, that is the standard pressure. Oh, no. What is 1 atmosphere equal to in moles? GM in moles. Oh. What is he talking about? A 10-liter container holds gas at 1.50 atmospheres and 300 Kelvin. The gas is heated to 450 K, changing the amount of gas or volume. Determine the new pressure using the ideal gas law. Oh. So how do we do this? 10 holds gas at 1.15. Yes, it's for it's changing a lot of gas or volume. One mole is 22.4 liters. So how many moles is that going to be? So we just have to divide to, to 22.4 liters. It's gonna be 10 divided by 22.4. Just making a solid guess here. That's going to equal to 0.4464285714 mole. So now we just have to solve. Okay. The gas determine the new pressure using the ideal gas law. Okay, so we're going to try to solve this as fast as possible. Okay? We just have this. Well, literally, just get the problem. Just get the problem. We're just going to get the problem here. So the ideal gas law. Oh, for crying out loud! I never even knew that this was possible. So we could just use the Gay-Lussac law. We could just use the Gay-Lussac law. Of course, this is the ideal gas law. We can just need to use this. But we can just use the Gay-Lussac law, right? Amount of gas stay constant because all this is two ways. Yeah, I think I'll just use the Gay-Lussac law because this is really just a Gay-Lussac law problem. So we have P1, T1. Yeah. P1, T1 plus P2, T2. I was trying so hard to solve it and convert all the unknown stuff. Only for this to be this. So we're trying to find the pressure, the the new pressure. So P2 is something just happened. P1 times T2. That's going to be 1.50 times 450 over T1, which is 300K. So we have 2.25 atmospheres, maybe 2.25 atmospheres. See if that's correct. Yeah, that's 2.25 atmospheres. I'm gonna go to the next one, which is the last one. Then just occupy. Try to find a volume here. we have PV equals NRT. So it's going to be P NRT. So 5.00 times 0.0825 to 0.5 600 times 600 over P, which is the pressure one. This is pressure one. Oh, I'm trying to find the pressure here. So 0.0. The answer is going to be 24.62. 24.62 meters. Yeah, it's correct. So now we're going to go to the second law that we're discussing is the Dalton's law, the law of partial pressures. Okay. So if you can see here, based on the kinetic theory of gases, the gas will diffuse in a container in space, blah 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 blah. So basically, it just says that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the gases in the mixture. So if you have a gas, see, if you have two gases in a mixture, the pressure, see, the pressure of each gas is going to be, you know, it's going to be summated. Okay, you're going to get the sum of both gases. Yeah. So you're going to get the sum of both gases, and that will equate to the sum of all gases. That's going to be Dalton's law. So we're just going to get the problems. Okay. So we have from the ideal gas law, the composition of the gas, we can write N total, Na plus N V. So P total, V again based on material, that's what we apply, so that equals the sum of the pressure function. Combination this. Yeah, so that's basically it. Just trying to find the problems, okay? So if you look at the problems, we can do problems here as well. Since we have part two here. So there is a mixture of a sample of gas A. Let's just look at one problem, okay? A sample of gas A evaporates through the water in a closed system. What's the pressure of gas A if the total pressure is 780 torr and water vapor pressure is 188 atm? Okay. So the solution here is to convert pressure to same units as so 780 torr divided by 760. So no. Whatever the torr is, we think that's 760 torr. That's going to be equal to 1.03. So subtract water vapor pressure. So 1.03. Okay, so the law of partial pressures. So let's try this. Let's see the second problem. There's a mixture of 4 moles of hydrogen gas, 8 moles of oxygen, and 12 moles of helium, and 6 moles of nitrogen in a closed container. What is the total number of moles in the system? So 4 plus 8, okay, 4 plus 8. It's going to be 12 plus 12, it's going to be 24, okay. It's going to be 24 plus 6, it's going to be 18. So we have 18 number of moles. Yeah, 18 moles. Is that it? I believe that. Oh, seems like so. That was actually 30. That's so dumb. Sorry. I sort of got a little bit confused in the calculation part, but it's gonna be 30 moles. It's gonna be very easy. So find them out. So let's try another example. That this is going to be Dalton's law. If there is a mixture of hydrogen and oxygen gas and container with 10 moles total, okay, and the mole ratio of hydrogen is 0.67 mole hydrogen to 1 mole total. So if you can see here, the mole ratio here, okay. So we're gonna see mole ratio of hydrogen is 0.67 moles, and the total of moles is one. How many moles of each gas are there? If we look at this, okay. So we have 10 moles total. 10 mole total. Here are 10 moles total, and times 6.67. That's times 0.67. Okay. Moles of hydrogen divided by. So this is just. Let me just hydrogen over 1 moles over 1 mole total. And that's going to be 6.7 moles of H2 gas. So if we look at the general formula, formula for uh, then we're trying to look at mole ratios. Mole ratio formula. For Dalton's law. This equation show it. So it's going to be like this. The mole fraction of a specific gas equals the moles of that gas. No. Mole fraction of a specific gas equals the moles of gas. Divided by 20 moles plus 25. So let's get a step by step. The mixture contains 2 moles of nitrogen and 2 moles of oxygen and O2. Total pressure of the container is 10 atmospheres. Find the mole ratios and partial pressures of both gases. So we have calculated total moles. To calculate the total moles, we have to get 5 moles, because there's a 2 mole, 5 moles, and 10 moles. Now find the mole ratios. So we have X and 2. It's going to be nitrogen, so XO2 and XO2. There's going to be 2 moles over 5 moles, and then 3 moles over 5 moles. So let's just. So 0.6 is it. Now you have to multiply it by the total pressure, which is 0.48 times 10. So be 4.0. So this is going to be the oxygen now. So when you get the mole ratio, you times it by the pressure, okay, by the pressure, and you're going to get the partial pressures of each of the individual sort of elements. So that's going to be it for Dalton's law. If you use that, okay, we're going to solve some Dalton's law problems here. It's very easy, very easy. Hopefully, I can solve it in a good, maybe good amount of time. So let's just solve a bit of problems. So that we have your container has oxygen. Is there 0.88 atmospheres, nitrogen 2.10 atmospheres, carbon dioxide, find the total pressure. You just have to add everything. So that's going to be 2.90 atmospheres plus 0.30. It's going to be 3.20 atmospheres. So let's check if we're right. 3.20. That's 3.20 atmospheres. No, yeah, we're right. So we have to find the mole stuff. Total pressure of a gas mixture is 5.60 atmospheres. Oxygen contributes 1.80 atmospheres, while nitrogen contributes 2.90 atmospheres. So the what is the partial pressure of argon? Wait, what is argon? What is argon? Let's check how to solve this. Argon molar mass. I guess we have to find out what the molar masses are. Mole, molecular stuff, molecular. How to solve this? I don't even know how to solve this. Let's see. So you have that. So you have to minus everything. It's partial pressure, total pressure, plus some non-partial pressures. Okay, I see. So that's going to be 5.60. We have to plus everything first. We have to add everything first. So 5.60 plus 1.80 plus 2.90. Then we have 10.3. So 10.3 minus there's partial pressure. There's a partial pressure of these. Oh, you have to get that. You have to minus everything, not add everything. Okay, so that's 2.90. And just get 0.9 atmospheres. 0.9 atmospheres. It's going to be correct. And this mixture contains yeah, so we just have to add everything. 0.45 plus 0.75 plus 0.30. That's going to equal to 3/2, which is 1.5 atmospheres. Okay, so let's check. Let's check what we're looking for. This 1.5, yeah. 1.5 atmospheres. So total pressure inside the flask. The total pressure inside the flask is 4.80 atmospheres. Find the pressure of neon. Okay, and we just have to 4.80 minus 1.25 minus 2.05 is going to equal to 1.5 atmospheres, or 1.50 atmospheres. It's just 1.50 again, so that's correct. That's correct, that's correct. Just add a 0. So I guess make sure this is the you see this. The gas mixture contains yeah, so calculate total pressure, just plus everything. Just add everything, bro. That's basically it. So we have 5.7 atmospheres. Check it. Correct. Calculate the total, so we're gonna have gas mixture has a total pressure of 760. So 760 minus 160 minus 40 is going to equal to 560 millimeters of mercury. 560? No, wait. Wait. 760 minus 160 minus 40. Yeah, 560 millimeters of mercury. Then we have this. So we just have to add the total pressure. 0.55 plus 1.10 plus 2.35. That's going to equal to 4 atmosphere. 4.4. Yeah, 4.0. So you have to add the zeros first. 4.00 atmospheres, and then we have this, a gas mixture as a total. So you just have to go 2.80 minus 0.55 minus 0.85. And that's going to equal to 1.4 atmosphere for nitrogen, and that's 1.4. Yeah, 1.40. So mixture contains gas. Yeah, so we just have to add everything. 1.40 plus 0.95 plus 0.60 plus 0.25. It's going to equal to 3.20 atmospheres. Total pressure is 900 millimeters mercury, so that 900 minus 300 minus 250, that's going to be equal to 350 millimeters mercury. So yeah, it's basically it for Dalton's law. Okay, now we're going to be talking about let me just check another example. Let's do number 3 here, because there is mole ratio. There's the most mole ratio that we're talking about. There's one problem with a mole ratio, and then we're going straight to Graham's laws, diffusion and effusion. So we have this. Oh, yes. Uh-huh. Then do this. What the? I think there's something wrong with this. There has to be something wrong with this. There has to be something wrong with this. Yeah, there we go. If there's a mixture of hydrogen, oxygen gas, and containing 10 moles total, the mole ratio of hydrogen and oxygen. So it's equal to 7 mole each gas, or the so just 67 mole for the hydrogen, then there's obviously going to be 100 minus 67. Okay, 100 minus 67. This is going to be 33. we have 33.33 hydrogen, oxygen, I mean. So then 60.6067 mole for hydrogen. So we have hydrogen goes, and over how many moles? 1 mole total. Then you times that. Okay. After you get the result from that, 0.67 moles times over divided by 1 mole is going to be 0.67 times 10, and that's going to be 6.7 moles of hydrogen. And we have oxygen. Okay, so we have oxygen. We have oxygen here. That's going to be 0.33 divided by 1. That's going to be 0.33 times 10 moles in total. That's going to equate to 3.3 moles. So that's going to be it. You can just see here for this problem. Yeah, we're just about that. Correction here. This is actually H2 and this is actually O. Just that's going to be it for mole ratios. Now let's go to the third law that we're going to be discussing today is Graham's laws of diffusion and fusion. Because we have diffusion is a gradual mixing of gases due to the motion of component particles, even in the absence of mechanical agitation such as stirring. The result is a gas mixture with uniform composition. Diffusion is also a property, but it was not earlier. Okay. So if we do this, okay, multiplying both sides by 2 and rearranging. Exercise working on atomic bomb, it's a calculation of fusion. Okay, so I'm actually going to save this for tomorrow. Okay, I'm just going to save Graham's law of diffusion and infusion for tomorrow because this is a lot of content and most of the things that we've done here so far is Dalton's law and the ideal gas law. Okay, so we're just going to save this for for tomorrow. Okay, so if you guys enjoyed this video, if you learned anything from it, please give me a thumbs up and subscribe. That would really mean a lot to me. If you guys didn't like the video, please give me your honest feedback in the comment section, and I'll be sure to read it. I'll be sure to read it. Thank you very much for watching, guys, and I'll see you in another video. This is Rich Andre, and I'm going to be signing off. So, but before that, okay, let me just see how to convert. This has really got me curious, right? There was something that I forgot. How to convert number of moles to density. How to convert density and weight to number of moles for ideal gas law. So we have density definition here. Just density equals total weight, mass over volume. So number of moles is equal to total weight over molecular mass of the gas, so molecular weight. If you know total weight and molar mass, you have 44 grams of carbon dioxide. If you already have the total weighted gas and you know to give you molar mass, then it is not required to find n. So if you have from G, okay, so molar mass is always going to be, I think, uh, when you're studying chemistry, okay, when you're studying chemistry in school, I think that's going to be included, I believe, the molar mass of any of the gases, okay. So converting density and total weight via volume, find volume, V equals P. So we have mass over density is volume. Weight, total weight over density is solved for n. So we have PV and RT. Since we don't know what the if you're given the total weight and density, you can first find the volume, then you start with or mass signal. First find the volume. Okay, so we can find a volume here. Oh, I see. That's how you find a volume. Okay, I think I get it. I think I get it now. So density is just mass over V. So if we're given the total weight and density, you can find volume. Oh, okay, I see. I think that's about it. Um, I'm just going to go get my notebook and try to see if I can expand on this any further. But yeah, never mind. I think that's okay. That's good. As long as I got like a general, sort of a general idea of how this works, you know. If you don't got, if you don't have the moles, if you don't have the volume here, then you can just get whatever substitute, okay, whatever substitute. You don't have the density, you have to do this, okay, mass over mass of mass of volume, mass of volume, but okay. If you don't have the moles, you just have to get the number of moles over. You just have to get the total weight in grams and the molar mass of the gas. So that's just basically it, you know. Uh, Mass over molecular weight for n. And that's going to be it. Um, Thank you guys for watching. Again, tune in for the final episode of this. There's going to be a final episode of this, including this and how to solve problems relating to Graham's laws of diffusion and fusion. Thank you guys for watching.